Okay, guys, so let's start. Okay, so good afternoon, everybody. So in the very beginning of this course, I told you what is the difference between microcontroller and microprocessor. I told you microcontroller is a complete system, This is the very beginning, right? So this is the time now to understand what I mean by complete system and how this can make programming easier, how this can make you can program big application, okay? How you are gonna understand it? You are gonna understand it now when I explain serial communication, because serial communication is a circuit. So here, this is a microcontroller, guys. You have microprocessor, as I explained before. You have RAM, you have ROM, you have buses, as I explained in the very beginning of this course. On top of that, you have some circuits here for serial communication. You have another circuit for timer system, as you will see. So this circuit should do some work. So too much work is going to be done at this circuit. You got what I'm saying? That means for the timer or for the SCI, you don't need to take too much time from the microprocessor because this circuit are going to do the work. Okay, so you will understand better what I mean if it is a complete system when I finish teaching SCI and timer system. So let's now focus on SCI. So as I told you guys, SCR this is a circuit for serial communication. Okay, this is SCI. It actually has two parts. One part for receiver, the other one is transmitter. Okay, so here receiver, and this is transmitter. And I told you our SCI is full duplex. Full duplex means you can transmit and receive at the same time because the circuit is repeated. So you have one circuit here and we have another circuit here. You have two circuits, right? One for receive, one for transmission. That's why you can transmit and receive at the same time. And you transmit or receive serial. I explained last time what I mean by a serial. So idea is very simple. I'm going to give you very high level description on how it works. Very simple. The way it should work, guys, is number one, similar to anything I explained before about interrupts, you should configure. So number one, you have to do configuration, okay? After you do configuration, I just want you to understand how this external circuit is going to make everything easy, because the transmission itself and the reception and the transmission is going to be done by the circuit. Just when you finish, microcontroller is going to just go and take the value from you. That's it. So the idea simply, guys, is for here, for the receiver side, you have here a buffer. This buffer is a byte. It's a byte, register a byte. Okay. So once this buffer receive 1 byte from here, the receiver is going to trigger interrupt. That's it. Okay. So you don't need to do anything. The external circuit is going to do everything. And after receiving 1 byte, the circuit is going to trigger interrupt. And all what you have to do here in the interrupt subroutine is you have to read this one. I have to read the buffer so that now the buffer is empty and is ready to receive another byte. That's it. You got what I'm saying? Why it's too simple? It's too simple because the difficult work already done by the hardware circuit. From the microcontroller point, from the microprocessor point of view, just it's interrupt. Once I'm interrupted, I'm gonna just read the register. After I read the register, I'm gonna take 1 byte received. Okay. Same thing for when you transmit. So when you transmit here, there is no interrupt for transmission, but all what you have to do to transmit some value is, number one, I have to make sure the buffer is empty. This is number one. Why you have to make sure it's empty? Simply because microcontroller is much faster than the SCI circuit. I cannot just overwhelm the SCI circuit with data. I cannot do that, right? So all what you have to do, number one, you have to make sure the buffer is empty. The meaning of empty is that it's already, you transmitted the already finished transmission, and now it is ready to receive another value. Okay. Once you make sure it's empty, just all what you have to do, you have to write 1 value to this register. That's it. That's it. And everything will be, the hardware, the circuit will take care of everything else. You understand what I'm saying? So very simple. All what you have to do, guys, now, before I show the program and give you the details, you have to do three things. Number one, configuration. Number two, for reception. All what you have to do just in the interrupt subroutine. Once you receive a data, the interrupt is going to be triggered, and then you have to read the data here in the interrupt subroutine. You have to read it from the register. Number three, for the transmission, you have to make sure the buffer is empty. Once it's empty, you just write the number or the byte you want to transmit, write it to the buffer. The hardware is going to take care of everything. You got what I'm saying? Very easy. So as you will see right now, but before, I'm going to go through this again quickly. For configuration, guys, the first thing you have to configure is what we call the baud rate. The baud rate is the speed of the transmission. So for example, you have some values here, as you see in this table here. I think for some reason, most of the people use this one. Maybe this is standard. So most of the people use this one, 9600. That means you are going to transmit 9,600 bits per second. Okay, for sure, the two devices should have the same. They should have the same speed, right? So you can program the speed. So we have different speed here, as you see. You can program it, and the way you have to program it, guys, very simple. You have 13 bits here, 13 bits, 0, 1, 2, 3, 4, 13 bits. These 13 bits are in two registers for sure, because every register is only 8 bits. Okay, so you have here a number 13 bits. Okay, so you have to write a number here, and based on this number, you can program the baud rate. So how can you get this number? I'm going to tell you easily how. You can get it from this equation. Yes, this is the number. Okay, so here, and this is, I'm going to tell you how it works, just to understand it. Number one, we have the system clock. We use this clock many times in this course, which is 24 megahertz. This is the system clock. We are going to take this clock, we are going to divide it by 16. So we're gonna generate another clock here. After you divide by 16, and then you are gonna divide it again by SPR, by the number you are gonna write. Okay, so you are gonna divide it again by SPR. After that, I'm gonna have another frequency here. Okay, so this frequency is the transmission. That means in every cycle you are gonna transmit 1 bit. You got what I'm saying? So that means, if you follow what I said here, this is the system clock, which is 24 megahertz. That means here in this table, I have two values, one is 16, one 24. I'm assuming we are going to work at 24 as usual, as we do. Okay, so I'm going to focus only on this column here. So that means if you need 300, so you have to put this value in SPR and so on. Again, we are going to select this value here, as you see here. So all what you have to do here, guys, you have to write this number here. Okay, so once you 156. So once I write this number here, I'm gonna program the baud rate to be this value. Okay, this is the first thing you have to do. Any questions? Okay, that's very easy. That's where I did here in the program. Again, nothing is new. As I told you, this similar to what we did for any interrupt before, guys. You have to write this one, because this is the interrupt. Similar. The only change you have is just this number, right? So this is for SCCI 1. I told you we have two SCCIs, as I told you before. We have SCCI 0, SCCI 1. Please don't program 0, because SCCI 0 is used to connect your laptop to the board. Okay, so this is how the coder can communicate with the board using SCCI 0. One more thing I said last time is this is serial communication. That means it usually is used if you need microcontroller to communicate with another microcontroller. Is that okay? Or it can be a device. This device, like a sensor or whatever, is going to communicate with microcontrollers serially. Okay. So how they are connected? Okay, as I told you last time, it doesn't matter. For sure, you can connect it using wire, or it can be connected using wireless. Okay, it doesn't matter here in the program if it is wired or wireless. It doesn't matter. Why? Because the only difference is that when we have SCCI 1, we are programming SCCI 1. Okay, and then if you put here a wire, so we are gonna transmit using wire. If you put here a chip, like a Zigbee chip, so it's going to be wireless. So here I'm programming SCCI once. That's why it doesn't matter if it's wired or wireless. I can use the same program for wired or wireless. You understand what I'm saying? So the way you have to do it, you should have a cable here. You connect one port to another port if you want to use wired. If you want to use wireless, so there is a chip, wireless chip. We call it Zigbee. You have to put the chip here, okay? And I think there is a jumper, as far as I remember, there is a jumper here somewhere to connect the output of SCCI1 to the Zigbee, okay? That's it. Is that clear? So what I'm saying, it's the same program here. It can be used if it is, it doesn't matter if it is wireless or wired. It doesn't matter, okay? Because we are programming SCCI, right? The output of the SCCI is, if it is connected to wireless or wired, it's not going to be reflected here in this program, okay? Anyway, so let's see. So this is, as I explained before, guys, this is for configuration of interrupts. I told you here for the baud rate, for example, if I have to write this number 156. So 156, so it has to be written. So again, because it has to be written in two registers, as you see here. This register SCCI1. As you see here, every register we have two of them, 1, 0, and 1. Okay, this is for SCCI 0 and SCCI 1. So I'm going to focus on 1 because SCCI 0 is already used by your laptop. Anyway, so here what I'm saying, we have 2 bytes, guys. We have here SCCI 1 BDH, this one here, and we have this one here. Okay, so this is a word. In this word, I want to write 156. 156 here. How I can do that? Very simple. So I'm going to write 156 here, and then I'm going to write 0 here, because this is a byte. This byte can store until 255. Is that okay? That's what I did here in the program, in the first part here of this program. As you see, good. See, guys? Yeah. So here I'm going to write, yeah. So this register is the most significant byte. This is the least significant byte. So here I'm going to write 156. Here I'm going to write 00. Again, guys, there is no need to convert it to hexadecimal. There is no need. Just put it in decimal here, and the code word is going to do the conversion, everything. Okay, so you don't need to bother yourself. So yeah, so this is how I can program. So here in this program, guys, see what I want to do here. I have 2 boards, one board and another board. What I want to do here in this program, I want to connect the 2 boards together so that here this board has a keypad and LCD. This one also has a LCD and keypad. Okay. What I want to do here in this program, when I press a button here in the keypad, I want to display it on the other LCD. When I press here a button, I want to see it here. So if I press here 1, I can see here 1. If I press here 2, I'm going to see here 2. Is that okay? So this is similar to the lab. This is similar to the lab we had before, but the lab we had before, when I press here any button, I'm going to show it in the same LCD, right? But here I want to use SCI so that when I press 5, I want to see 5 on the other one. Is that okay? Also, I added one very interesting problem in the assignment regarding this. I think here you can send to command. Okay, for example, I have another board somewhere. When I type a button here, I can send a command to do something. Okay. Anyway, so also if you send any number, I have to see the number on the LCD of the other board. Also, if you send asterisk, it's gonna clear the other one. Okay. So again, very simple. So here, one keypad is gonna control the LCD of the other one. Okay. So here I should use either asterisk to clear the LCD or use a number to display the number. Is that okay? So, okay, very important thing. Look here, guys. The same program, I'm gonna run it on the 2 boards. The same program. You understand what I'm saying? It's gonna work. The same program. Okay, as you will see right now. Anyway, so number 1, as I told you guys, I have to program the baud rate. Okay. So try to imagine it with me. This program, I'm gonna run it on the 2 boards. Okay, you'll understand. So that because both of them are doing the same thing. So try to understand it. Okay. So this is number 1. Okay. Number 2 here also I have to program this one in order to enable transmit and receive. So if I go to this one, CR2. Yeah, this one. As you see here, guys, this register, we have here this bit. Okay. And this bit. So this bit for transmitter enable and receiver enable. So you have to put here one, you have to put here one to make sure to enable the circuit, the transmission and the receiver. Is that okay? Also, this one is the enable bit. You know, any interrupt, we have enable bit. Okay. We had enable bit in IRQ, RTI, in the timer system. Every interrupt we're gonna have enable bit. So it's the same thing here. So if you want to disable the receiver interrupts, you just put 0 here or you put 1 here. Okay. So anyway, so I have to program this one because the transmitter and the receiver are not gonna work unless you enable it here. Okay. So that's what I did here in this one. So I enable the transmitter and receiver. Also, I enable the receiver interrupts. Okay. So the last thing I have here, okay, you have the option here in this one, yeah, to select. I told you the data you can transmit 8 bits or 9 bits. So the data, every time I transmit a character or I transmit information or data, whatever you want to call it. So the data I transmit, it can be 8 or it can be 9. So I select just 8 because the ASCII codes, because I'm going to send ASCII codes. All the ASCII codes are 8. That's why I'm going to put here 0. That's what I did. Okay, so what I did here, I just configure it 8. Sorry, yeah, here. Okay, guys. So now after what I did here, so now that's it. Now the transmitter and receiver is ready. Okay. Again, I'm going to repeat it again because it's very important thing you should understand, guys. Okay, listen to me. We are going to do something too complex, too difficult, but we are going to do it easily. Why? Because most of the work are done by the external circuit. That's what you should understand. If you look at the code is very trivial, very simple, because of the most of the work is not done by the microcontroller. Most of the work, if the microcontroller has to do it, it's going to be terrible. It's going to be not terrible. It's going to take too much time. Similar, if you want to understand better, similar when in chapter 3, when you used the microcontroller to program 1 second. Do you remember? So I had delay YMS. When we had delay YMS, so microcontroller has to count for 1 second. So this was not a good idea because microcontroller was busy all the time, right? So I cannot do anything else. I cannot have a big application. However, when case of RTI, all what I did just interrupts. So I'm going to take 8 interrupts for 1 second, right? Because the counting are not going to be done by microcontroller. The counting is going to be done by external circuit. So the same thing here. The transmitter, the receiver is going to be done by the external circuit. Okay, it's the same thing you will see in the timer system. The same idea. When I explain the timer system, you will see we are going to do something very complex, but we are going to do it easily because most of the work is not done by the microcontroller. It's done by external circuit. Anyway, so let's see. So now look here, guys. So now this is the configuration you have to do. This is number 1 configuration. Number 2, okay. Now I want to transmit. Okay. In order to transmit, all what you have to do here, guys, I told you, if you want to transmit, again, this is SCI. We have 2 parts. We have transmitter and we have receiver, right? All what you have to do here, if you want to transmit, you have a buffer. Okay. This buffer is going to be this. You have to put information here. You have to put a data here, and then this data is going to be shifted bit by bit and to transmit it. Okay. So all what you have to do, number 1, I have to make sure this one is empty. Number 2, once I know it's empty is just I'm going to write a byte to it. That's what I did here. Number 1, how I can know it's empty? Because again, you cannot overwhelm the transmitter. Take this data, take this data, take this data. Okay, so because microprocessor is faster, that means before I give a new information or a new byte, I have to make sure the transmitter already finished the last one. Okay, how I can do that? Very simple. So the way you have to do it, guys, in this register here, it's the last bit. So the last bit here, it can tell you if it is empty or not. Okay, so if you go to this one, yeah, this bit here. Okay, so using this bit, you can know if it is empty or not. So that's what I'm going to do. As long as it is, I think 0 means it is not empty. as you see here. See what I did here? So as long as it is 0, that means it's not empty yet. Okay, so that means I have to wait. That's why, as you see here, guys, I have to keep looping here until it is 1. 1 means it's ready. Okay, so now if it is ready, all what you have to do, the data you wanna write, you wanna send, just write it to this byte or this register. That's it. So what is this register? What I call it a buffer. So what is this register? The register is SDIGL, this one. Okay, that's it. So whatever you want to send, but first I have to make sure the buffer is empty. This is number 1. Number 2, once I know it's empty, just I'm gonna write it here. And similar the way it's the same instruction we used to before to program DDRA, port B, same thing, because all these registers, as I mentioned very early, nothing is new. All these registers have addresses, like memory location addresses. So every instruction you used to before for memory, you can use it here. So what I'm gonna do here, guys, once I know now it is ready, it's ready, I can transmit. So I'm gonna get one number from the keypad, and then I'm gonna transmit it. That's it. And then I'm gonna loop back again to here. Very easy, right? So here, this is one part. So here I'm gonna keep looping in this part. Every time I'm gonna wait until the buffer is empty. Once it's empty, I'm gonna take a value from you, okay, and then I transmit it. Is that okay? As you see here, this is how can you transmit. Very easy, right? Now, in the receiver, when you receive, okay, again for receiver, I don't need to check if because we are gonna have interrupts. Okay, so I need to check. I don't need to check. I don't need to ask the receiver, have you received any data? No. Have you? I don't need to do boolean here, okay? Because I have interrupt. That means once the receiver receives a byte, it's gonna interrupt me, right? So once you have interrupt here, what it means? When you have interrupt here, what it means? Simply, when you have interrupt here, it means the receiver received a byte, go ahead and take it, right? So where I have to take it, I'm going to tell you how, where, because I told you we have here a receiver part. The receiver should have here a register, okay? So once it receives a byte, it's going to trigger interrupt. Okay, all what you have to do just to go and read this value. That's it. Very easy, very simple. Again, because we didn't do anything, because the work is not done by the microcontroller. The work was done by the external circuit. Anyway, so what is the name of this register? I have to read. This is the name of the register, SCI1 GRL. If you see here, this is the same name like this one. Do you mean you are using one register for transmitter and receive? You understand what I'm saying? So it's the same name. Okay, no, we actually use two separate. Okay, because I told you we can transmit and receive at the same time. That means we have two of them here, one for transmit, one for receive, okay? But both of them have the same name. Both of them have the same name, okay? But if I wanna write, it's gonna write here for this one. If you wanna read, because one of them read only, the other one is write only. You get what I'm saying? So don't be confused. Yes, it is the same name, but it is two different, two separate, because this is a full duplex. That means I can transmit and receive at the same time, okay? So here, what you have to do, guys, very simple. Look here. Once there is interrupt, that means there is an information ready, or there is a byte ready for me, I have to take it. That's it. So here I'm gonna read this one this way. Once I read it, I'm gonna compare it to asterisk. I'm gonna compare it to asterisk, okay? And then if it is not asterisk, I'm gonna come here to display it, okay? Because I told you I should send either a number or ASCII. So here I'm gonna compare it to ASCII, to asterisk. If it is not asterisk, so I'm gonna come here to display it and then leave. I'm done, okay? If it is not asterisk, if it is asterisk, that means I have to clear the LCD, okay? That's why I clear the LCD this way here, okay? Any questions? Very easy, very simple. Okay. One thing is left. What is that? What is left? Again, as I mentioned very early, for any interrupt, I have to clear the flag bit. You have to clear the flag bit. right? You have to do that. You have the only exception, as I said before, IRQ. Any other interrupt, you have to clear the flag bit. Okay. So how can you clear here the flag bit? For sure, the flag bit here is in this register SCI1 SR1. Yeah, this register. Okay. So this is this is the flag bit. So the flag bit is here. Okay. Yeah. So this one. So in order to clear the flag bit, you can do one of two things. For sure, you can write here 1 as we did before. Okay, this one thing you can do it. The other thing you can do, you can read this register. Once you read the register, automatically it's going to be cleared. Okay, that's how it is. You got what I'm saying? So you just read it. You don't need to do anything with it. Just read. Once you read this register, this one is going to be cleared. That's what I did here. If you see what I did here in the code. Oops. Look, guys, here in the first instruction, I just read the register. Just read it. I didn't do anything with this value, okay? Because I'm reading it because I want to clear. Okay. Anyway, you can again. There are two ways to clear the flag bit. One way, you can just read the register, or you can put one here in this register to clear the flag bit. Okay. Any question, guys? Okay. In C language, how can you do the same thing in C language? Okay. So similar to what we did before, guys, for C language, you have to use a number here. You remember this number? Same thing as we did before. Here should be 21. And I told you before, how can you get this number? So if you go to the table here, you remember you used to use number 6, number 7, and in the timer system, we are going to use different number. It's the same thing. That's what I told you in the very beginning. Once you understand how can you program one interrupt, all of them are the same, right? So what we did here, you remember? So this one, I think it was 1, 2, 3, 4, 5, 6. I think we started from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this 20 and this one is 21. Okay, that's why here I use the number 21. So 21 means SCI1. Is that okay? Same thing. So until now we used the number 6, used the number 7, and now I'm going to use 21. And just when I go to the timer system, we're going to use these numbers. Okay, 7, I'm going to use 8, 9, 10, 11, and so on. So very easy. Okay, just we change some numbers. Anyway, so for the interrupt subroutine, you have to use number 21 just to tell the C language. This is the interrupt subroutine for SCI1. Okay, this is number 1. Okay. Let's see here the initialization. So here, this is just for keypad. Okay. This is again in C language, similar to what we did before. You can use functions, or you can just write to register as we did in assembly. Okay, as we did before. Here we have a function initialization for SCI1. All what you have to do here, guys, just to give me the baud rate. You don't need to worry about anything. Just give me the baud rate, and then I will do the conversion. I'm gonna come up with the number. The number I used here. You remember this number? Yeah. So just to give me this one, and then I'm gonna get the number here. Anyway, so that's all what you have to do. So here in the initialization, just you have to do this one. Okay. Here I do initialization for LCD and so on. Okay. Now let's see how can you transmit and how can you receive. The way you can transmit is everything is done here. So you just call the function. This function is going to do all the initialization. Okay. In order to transmit, guys, we have a function here. You don't need to do anything. Just you have a function here. This function is called output character 1. Okay. All what you have to do, just to give me a character here, and inside this function, everything will be done. What do you mean by everything? I mean, inside this function, these are the details. These are the details. Inside this function, the function has to make sure, has to wait until the buffer is empty, and then it's going to write this value to this buffer. Is that okay? So very simple. In C language, you just whatever you want to send, just put it here. So what I did here, guys, I'm going to get a number from the user using get key. Okay. And then I'm going to convert this number to ASCII, and then I'm going to send it to output character to transmit it. That's it. So you have a function, just to give the number. The function is going to take care of everything. Okay. This is for transmission. For receiver, This is the interrupt here. Every time there is a byte, every time the receiver receives a byte and the byte is ready for you, you just this interrupt subroutine is triggered. So all what you have to do, just read this value and that's it. Okay. So how can you read this value, guys? As you see here, we have another function. As you see here, you just read this function. So what I did here, guys, I'm gonna call this function. This function is gonna return once I call this function. This function is gonna return the byte we received. It's gonna also clear the flag bit, everything. Okay. So inside this function also is gonna clear the flag bit. You just call this function. This function, you are gonna get a byte. You put it here in character C, and then I convert this byte to ASCII. And then I'm going to compare it to I want to check if this value is for asterisk or not. If this value is asterisk, so I'm going to clear the LCD using, number one. Number one here, this is a command. Instruction 8. This one is used to transmit a command. So now, if C is asterisk, I'm gonna come here. If it is asterisk, if it is a number from 0 to 9, I'm gonna come here. So if it is a number, all what you have to do, I'm gonna display the number. If it is asterisk, I'm gonna clear LCD. That's it. Okay, guys. Any questions? Again, you can extend. This is just very simple idea. You can extend it. You can extend this idea for sure. So now, for example, you can assume every keystroke here is a command. Okay, for example, I want to control something. You have a board. The other board is connected to a motor, is connected to buzzer, is connected to whatever, and you want to control it remotely. You can do that, right? So and I think I did one question in the assignment is something like that. So for example, one means turn LED on or turn the light on. Number two, stepper motor has to move, whatever. You got what I'm saying? Anyway, it's very easy. Any question, guys? Okay, great. So now, what I'm going to teach right now, I'm going to teach the timer system. Okay, you are not going to see, yeah, for sure, the timer. This system is going to do something completely different from SCCI, but programming wise, it's going to be the same thing. I'm going to just repeat the same thing. Okay, so it's still the same idea, guys. Inside the microcontroller, we have a hardware circuit. We call it timer system. Okay. Most of the work is done by the timer system. Okay, we are going to get very little time. This is the key. This is what we should learn in this course. We are going to get very little time from the microcontroller. Okay, because of interrupts, but most of the work are going to done by the timer system. Okay, without the timer system, for sure I'm going to teach right now how you can use the timer system. Okay, but if you want to do the functionality of the timer system using the CPU, is going to take too much time, right? But the beauty here is most of the work done by the external circuit. That's why you can make big applications. Is that okay? As you will understand now. So it's external circuit, and this same thing, believe me, just you need to do configuration, and then you are going to have interrupts. That's it. Okay, same thing. So now I'm going to go to the timer system and then explain how it works. And even programming the interrupts will be same thing, just changing. We're going to change numbers. So now let's talk about the timer system here, guys. So in our microcontroller, we have here a circuit. This circuit we call it timer system. We have another circuit, we call it pulse width modulation. I'm going to talk about this one as well. Pulse width modulation. Okay, this is separate. These are two separate things. Okay, don't be confused. They are two separate things. Okay, and there are other things, by the way. So, for example, we have, I think, analog to digital, something that we have other things for sure in this course. I'm not going to teach everything, but at least if you learn how can you program one system, all of them almost the same. Because as you see right now, is all what we do is interrupts, regardless of how the system is. Similar, exactly, regardless of the system, what we are going to do here is similar to what I explained in SCCI. Number one, you have a number of registers, you have to write to registers for configuration. Number two, you have interrupts. That's it. Okay. Anyway, so now I'm going to talk about the timer system, and then after that, when I finish, I'm going to talk about pulse width modulation. Let's now focus on the timer system. So first, what's the timer system and what functionality it can do? I'm going to explain to you. Look here, guys. In the timer system, as you see here, we have 8 channels. 8 channels. Okay, channels. Every channel has a pin, as you see here. So we have 8 channels, as you see here. Every channel has external pin on port T. Okay, so T0, PT0, PT1, PT2, and so on. So here, every channel, we have 8 channels. Every channel has an external pin. Okay, because it has external pin, so we are going to use this pin somehow. For sure, we are going to use it, right? You will understand now. This is number 1. Number 2, every channel, it can be programmed to work input capture or output compare. So I have 8 channels. Every channel can do one of functionality, one of 2. Either you can program it, right? So similar when we program ports, input, output, input, output. It's the same thing. So if you need too many input capture, you can program all of them input capture. If you need too many output compare, you can program all of them output compare, or one input capture, one output compare, whatever you need. For sure, I'm going to explain what I mean by input capture, what I mean by output compare. Okay, so here the timer system can be used to do input capture or output compare. Okay, so I'm going to explain what is this for sure. But you can program every channel to do one of them, only one of them at a time. So at a certain time, similar to the pin, when you program a pin, this pin can be input or output pin, right? At a certain time, input or output, same thing. Okay, anyway. So as you see here, guys, so we have 80 channels. Every channel has a pin, okay? Also, every channel can trigger interrupt. This is one more thing. So now we can have 8 more interrupts. We have interrupt can come from channel 0, channel 1, channel 2, until channel 7. Okay? So every channel, we have 80 channels. Every channel can do either input compare or output capture. Every channel has external pin. Every channel has interrupt, can trigger interrupt. Is that okay? For sure, I'm going to say, why do you need interrupt? You should understand why, right? Because interrupt means there is an event, right? Similar to SCCI. SCCI, the event was the receiving or the receiving a byte. When I receive a byte, this is the event. So I have to trigger interrupt, right? Yeah, for sure, there should be an event here. I have to explain what is the event that is going to be used to trigger interrupt. But okay, let me complete description. On top of that, we have a number of registers. We have a number of registers to control the operation of the timer system. Is that okay? On top of that, we have what we call 16-bit counter. Counter, you can tell from the name, counter. So only one, don't be confused, because yes, we have 80 channels, but we have only one counter, one, right? And this counter is 16-bit, right? And now I want to explain how this counter should help the channels to do input capture or output compare. How I'm going to explain now. So now I'm going to connect everything together, okay? But before I connect everything together, I just want you fully understand, because this is the most important thing. What is, before I give you the details, okay? So what is input capture and why this timer system is going to do input capture very efficiently, comparing if I do it using the microcontroller. Same thing. What do you mean by output compare and how this is different from what we did before? Let's start with input capture, okay? I'm going to make it for sure. Before I go to the details, I want to explain what I mean by input capture and output compare, okay? Look here, guys. In many cases, I want to measure time. I need to measure time, okay? What do you mean by measure time? For example, I have a signal like this one, and I want to measure the time from here to here, okay? Or I have 2 signals this way, as you see it. I want to measure the time difference between them. Or I have a signal like this one. I want to measure the time from here to here. Is that okay? Let me say it again. In many cases, I want to measure time. Okay? Either it is signal this way, or I want to measure time from here to here, or I want to measure time from here to here. Is that okay? The question is, how can I measure the time efficiently, easily, with taking very little time from the CPU. How I can do that? Okay, input capture. I see, input capture. So input capture is made so that it can measure time efficiently. Is that okay? Using input capture, you will see. I'm going to give you more details, but just keep in mind, every time you want to measure time, for example, the time difference between two signals, or the time from here to here, or time from here to here, the best way to do it, the most efficient way to do it, is using what we call input capture. Is that okay? So input capture is invented, or this is the main functionality for input capture. Don't think about it. If you want to measure time in a signal, input capture, done. Is that okay? So now let's answer another question. Why you need to measure time? If you have a signal like this one, for example, why I want to measure this time? I'm going to tell you why. Okay. For example, I'm going to go to a specific application. Okay. Yeah. Here, guys, in the distance measurement. Okay, this I told you this is in this sensor. What's called ultrasonic sensor. This sensor is used to measure distance. Okay, the way it works is it comes with two pieces, as you see here. One is transmitter, one is receiver. Okay, so one of them should transmit ultrasound sound wave. Okay, so when the sound wave hits an object, it's gonna come back to the receiver here. Is that okay? So one sensor is gonna transmit ultrasound, the other one is gonna receive the return. Okay. All what I want to do, I want to measure the distance from here to here. I want to measure the distance. Okay, guys. As you know, there is a relation between velocity and the distance and time, right? You know that velocity should equal distance divided by time. Is that okay? So for velocity, I know the velocity. Why? Because this is the velocity of the sound, which is known value. I think it's 334. You can check. I'm not quite sure. I think it's in this range, 334 meter per second. So this is the velocity of the sound. It's known value, right? So this is the velocity for the signal to go and come back, right? Sorry, this is the velocity of the signal, right? So this is the velocity of this signal, sound signal. Okay. Now I want to measure the distance. So the distance here is unknown. Okay. So now I know the velocity, the distance is unknown, so I need to calculate the time. Okay. So all what you have to do, guys, I wanna calculate the time for the signal. Oh, I'm gonna tell you how, but you will see right now. So the signal is gonna go hit and come back. Okay. So I'm gonna calculate this time. And then you have to divide it by 2. Why? Because this is the time for the signal to go and come back. That's why you have to divide by 2. So the question is, in order to measure the distance between, so this is how it works. So this is transmitter, this is a receiver, G and R. So transmitter is going to send a sound. This sound should hit object and come back. Is that okay? So in order to get all what I need to calculate, I need to calculate the distance here. The distance should equal velocity times time, right? So the velocity is already known, 334. I guess you need to check online, but I think it's this range. Okay, and then the distance is unknown. All what I need to know, I need to get the time from here to here. Okay, so what I'm gonna do right now, I'm gonna measure the time to go and come back. The time from here, from this time until I receive it back. Is that okay? And then I'm gonna divide by 2 to get the time. This is how we can measure the distance. Is that okay? So now the question is how I'm gonna use it. I'm gonna tell you how. Very simple. So the way you have to use it, guys. Number 1. This one has a pin. It's connected to microcontroller using one pin. This one also has a pin for the receiver. All what you have to do is here. This is transmitter. Every time I want to do measurement, I have to generate a pulse this way. Yeah, that's easy to generate a pulse, right? It's just one pin. This pin high for some time and then low. That's it. So every time you generate a pulse this way, and this pulse, let me go back. This pulse should be 10 microseconds, I guess, minimum. Minimum should be 10 microseconds. So this is just one pin. Okay. So every time you generate a pulse, you trigger the transmitter to transmit the signal. Is that okay? Not only that, the receiver here, once the transmitter transmits the signal, is gonna pull this pin high. Okay. So once the transmitter transmits a signal, it's gonna pull it high. Once the receiver receives it, it's gonna pull it low. Is that easy? So let me say it again quickly. Number one, all what you have to do, guys, after every time, I think it's here as well. So if you see here, every time I want to do measurement, I have to generate this pulse here on the transmitter. Once you do that, the other pin for the receiver, here, once the transmitter sent the ultrasound, is gonna pull this pin high. Is that okay? And then once I receive the signal, is gonna be low. Okay. That means the time for the signal to go and come back should equal the time from here to here. That means I need some way to measure. I have a pulse. I need some way to measure this time. So that once I measure this time, I'm gonna divide it by 2. And then I use it for measurement. Is that okay? So this is I want to tell you why in many application or in some application I need to measure time, because this time means something. Okay. I have another application, but I'm not. It's about cars. I'm not for sure. I'm not mechanic. I just know how to drive cars, so I don't know how they work. So in this example, I read it one time, but it's hard to me to understand it. But I'm going to tell you how the idea. The idea is that you have something like you have when you burn the gas, you have to input a certain amount of air and a certain amount of gas. So you have like you can measure. So this signal is you can have like some kind of 2 signals this way, and you can measure the time difference between them. And based on this time difference, you can know like the efficiency of the car or something related to that. Anyway, so what I want to say, guys, we have a signal. You are going to measure the signal, but we're not measuring the signal to do like a scope or do like a measurement device. We're not measuring it because I'm interested in measurement. I'm measuring it because this will help me to get some physical value or to get some information about the system. I give you one example here, and there are many examples. Okay, I give you one example. In case of the ultrasound, I want to measure the time from here to here because this time can help me to measure the distance. Is that okay? So now the question is how I can measure the time from here, this time from here to here. What is the easy? For sure, my CPU can measure it for sure. There is some way that I can use the microcontroller to measure it, but it's going to take too much time from the microcontroller. Is that okay? So how I can do it efficiently? So this input capture can do that. Is that okay, guys? Any questions? So every time again, I want to say it for the last time. Every time you want to measure a signal, you input capture right away. Okay, either one signal, or I want to measure the time difference between 2 signals. Okay, you have 2 inputs. Okay, 2 signals. Anyway, so input capture. Okay, this is how input capture can be used. For sure, I'm going to tell you how. Also, keep in mind, and this is the beauty of these topics. The beauty is I want to measure the time with very little time from the CPU, because the CPU itself can do the measurement. Okay, but the beauty here, because most of the work is going to be done by the external circuit, so I want to take very little time from the CPU. This is the key point here. Okay. Okay, this is what you mean by input capture. That's great. Now let's talk about I told you in this timer system. Now you can understand why you need a pin here. I need a pin so that you can apply the signal here. The signal I want to measure can be here. Okay. Anyway, so here what I'm saying here is now I explained input capture. Okay. Now I want to explain output compare, because I told you every channel can do input capture or it can do output compare. Is that okay? So what is output compare and when? Input capture is easy. Every time I want to measure time, input capture. Don't think about it. Okay. Okay, now what about output compare? When I need output compare, okay? So I'm going to explain to you how when we do output compare, and also I'm going to tell you something very interesting. Okay, look here, guys. In many in digital systems, in microcontroller, in digital system, in many cases, we want to generate signals, right? We want to generate signals. We do it a lot in any digital system or any microcontroller. In many cases, in many applications, I want to generate signals like this one, okay, square signals. We do it all the time. Is that okay? Like you remember the buzzer. When we did the buzzer, we just generate a signal like this one, and many other applications. So usually we need some way to measure or to generate signals like this one. Okay. Now I'm gonna make a very interesting comparison between 3 ways. How can you generate signals like this one? Okay. I'm gonna tell you 3 ways. One way here, as we did in chapter 3. Okay. What we did in chapter 3, pull high, right? Wait some time, pull low, wait some time, okay? With some time, okay? And then repeat again. So that's what we did in chapter 3 in the flashing LED, right? Pull high, wait, pull low, wait, and so on, okay? For sure, this is not a very good idea to do this way. Why is this not a good idea? Because CPU, I'm gonna take 100% of the time of CPU. Is that okay? That you should understand. So because when I take very little time from the CPU, that means I can do big application. CPU can do a lot of things. You get what I'm saying? So for sure, this is not a good idea because CPU is gonna be busy 100% of the time. If you have other things, you cannot do it, right? The other thing, we can do it using output compare. So output compare is used if you want to generate a square wave like this one, but much more efficiently than this one. Much more efficient than this one. Is that okay? So here, to generate a signal like this one, guys, we're gonna have one interrupt here. In this interrupt, I'm gonna set the time for the next one. So I'm gonna say to the pin, please toggle after this time. So we're gonna have another interrupt here, another interrupt here, another interrupt here. This is all what I need from the CPU. So instead of taking 100% of the time from the CPU, no, I need some very little time from the CPU here to serve interrupt. In this interrupt, I have to say you have to toggle after a certain time, or you have to toggle after a certain time, and so on. So all what I need from the CPU, little time here, little time here, little time here, little time here. Is that okay? By the way, this idea is very close to test 2 when you used RTI to generate a signal for the buzzer. It was very close idea. So I used RTI like output compare. Yes, you understand? So this idea is very close. It's the same like when in test 2 when you used RTI to generate a signal. Okay, but here we're going to use output compare, and the output compare is much better than RTI. Why? Because if you remember, I told you the main problem in RTI, we don't have flexibility when you set the time. We don't have flexibility when you set the time, right? You will see, and I told you, if you remember, when I come to chapter 5, I'm going to explain something much better than RTI. You have too much flexibility. If you remember, in RTI, you just have a table, and you have to select some values from this table. That's it. You got what I'm saying? So you don't have much flexibility, but you understand what I mean better when I explain it here. Okay. So anyway, so again, output compare is used if you want to generate a square wave this way, guys, efficiently, because here, from here to here, I need some time here for interrupt, some interrupt here, some value for interrupt here, and this is similar to the idea when you used RTI to generate a square wave in test 2. Is that okay, guys? This is what output compare is. So output compare is used if you want to generate a square wave. Okay. Input capture is used if you want to measure time. Is that okay? The last thing we want to do, and it's really very, very interesting, it's a pulse width modulation. Okay. Pulse, again, don't be confused, because in this chapter, I put the timer system with pulse width modulation. These are two separate things. No relation between them, two separate things. So pulse width modulation, guys, is, again, it's a circuit. This is a microcontroller. We have here circuit for pulse width modulation. Okay, very interesting. So all what you have to do, guys, here, microprocessor has to initialize, or has to do configuration to the pulse width modulation. So for example, in the configuration, I'm going to tell the pulse width modulation, I want to generate 1K hertz signal. Is that okay? For example, so you need to do some initialization. And this is the beauty here. So after you do the initialization, how much time we're going to take from the microcontroller? Zero time. Because once I initialize the circuit is gonna generate signal by itself without the intervention of microcontroller at all. You understand the difference? So here's the difference here, guys. The microcontroller is involved here for interrupt. For sure, that's much better than this one, for sure. But still, here in every transition from low to high or high to low, there is an interrupt. In this interrupt, I have to write a couple of commands to set the next toggle, when the next toggle is, right? So I need here in every transition, I need little time from the CPU here. Here, once you do the initialization, the signal is going to be generated forever until you decide to turn it off, with zero time from the CPU, without the intervention from the CPU. This is not only that, this one in pulse width modulation, it's you can still, from the name, pulse width modulation. Okay, you can control the duty cycle easily, as you will see later. Duty cycle, it's very trivial, very easy in programming to control the duty cycle. You know, as I taught before, in duty cycle, it's how much high comparing to the whole. For example, this one can be like 10%, but if the high is too much, something like that, this is 90%. If it is 50-50, should be 50%. So 50% means the high and low are at the same time. This 50%. Okay. So in some application like stepper motor and other application, as when I come to pulse width modulation, I'm going to explain it. We need something like that. I need some way to control the duty cycle easily. Pulse width modulation can do that. Any questions here? So again, guys, let's summarize what I said, because I'm going to build on what I said right now. Again, in digital system, in many application, we need to generate a square wave. To generate a square wave, we did something in chapter 3. For sure, this was not the best way to do it, because the CPU is busy 100%, because the generation itself is done by the CPU. Again, the same concept is repeating. I'm going to repeat the same concept. What is the concept you mean here? The concept is, instead of doing the work by the CPU, I'm gonna have external circuit to do most of the work, and then it's gonna just trigger me to take as little time as possible from the CPU. That's what I mean. So here the CPU can generate a square wave, but for sure it's gonna take too much from the CPU, which is bad. Why it is bad? Because I want to make big application. If just to generate a square wave, I'm going to take too much from the CPU. Okay, what about the other things? If you have a fire alarm, if you have a buzzer, if you have too many things to take care of. Okay, so anyway, so that's not good. The other idea is that you can use interrupts in case of output compare. So here, as I told you, have interrupt here, interrupt here. In every interrupt, you have to write some commands to set the time for the next toggle, right? As you will see. So here, this one much better than this one, because here all what I need here, little time here, little time here, little time. And this is similar to what you did in test 2. In test 2, you had interrupts. Is that right? It was better than this one for sure. Anyway, so this is another idea. The third idea is pulse width modulation. What's really interesting about pulse width modulation, two things. Number one, once you do the initialization, and you know, initialization will be similar to what we did before. You have just a number of registers. You have to write some numbers in this register. That's it. You get what I'm saying? So similar to what we did before in most of the topics we had here. So anyway, so once you do the initialization, okay. So again, the microcontroller is not there is no intervention from, I don't need any time from zero time. I don't need anything. After the initialization, this one is going to generate a signal until you decide either you change the frequency or you want to change the duty cycle. In this time, microcontroller has to go and write some values to the registers, okay? But to generate the signal itself, microcontroller doesn't need to do anything. Very interesting. You have external circuit. All what you need, just set, you initialize the circuit and then leave the signals. It's going to generate signal forever, okay? So now, so let me tell you the conclusion to proceed. The conclusion is, guys, now you should understand we have a timer system. In this timer system, we have 8 channels, as you see here. Every channel can be input capture, output compare. Every channel need a pin. Now you should understand why you need a pin here. We need a pin because if it is output compare, that means we are going to generate a signal. So the signal is going to be generated in the pin here. If it is input capture, that means we are going to measure a signal. That means the signal has to be here on the pin here. Is that okay? So again, as you will see, this is something you can program. So I can program every channel to do input capture or output compare. So it can do one at a time, okay? So again, they made it this way just for flexibility. So flexibility, that means in one application, if you need too many input capture, you can make all of them input capture or all of them output compare for flexibility, okay, guys? Also, we have here, everyone can trigger interrupt. You will understand more the details, okay? Also, we have here some register to control the operation. Also, we have here a counter, 16-bit counter, and this counter is going to play only one counter. For the 80 channel, we have only one counter. And this counter is going to play a major role in the operation of the input capture and output compare, as you will understand now, okay? But anyway, so now, guys, we have eight more interrupts here, 8 more interrupts. Any questions? Okay. Now, let me tell you something before I give you more details. I told you guys, we have 8 pins on port T, 8 pins, okay? Every one, it can be input capture or output compare. Okay. Now, let me ask you a question. By the way, before I continue, sorry. So, by the way, input capture can be twisted, as I'm going to explain later. It can be twisted to be like IRQ, as you will see later. So now, so input capture, I'm gonna twist it a little bit to do IRQ. I'm not gonna measure time, but it's gonna be similar to IRQ. So if you don't need to use all of them for input capture, output compare, you can use, again, they are designed to be input capture, output compare. However, if you don't need all of these input capture, output compares, so you can use one of them, like you can twist input capture to make it like IRQ, as I'm going to explain later. So now I taught in chapter 4, I taught 1 IRQ. Now you can have up to 8 more IRQs. Is that okay? Details are coming. I'm just giving you the big picture. Details are coming. This number 1. Number 2. Also, I can twist output compare. I can twist output compare to be like RTI. So now you can have also 8 RTIs. Okay. Again, here I'm not, listen to what I'm saying. Here I'm not using it as output compare. Here I'm not generating a signal. I'm saying I'm gonna twist it. As I will understand later. So now, guys, every channel is designed to do input capture, output compare. However, we can twist it to be like IRQ or like RTI as well. So now we have 9 RTIs, 8 here, and we have another RTI in chapter 4, and now we have 8 IRQs if you want. Is that okay, guys? Now, assume I don't need all of them I don't need input capture, I don't need output compare, I don't need more IRQ, I don't need output compare. Okay? If this is the case, you can use the pin here. You can use this pin as a general purpose pin, like port B, like port H, like port A. It can be general purpose pin. Just one pin. You can configure this pin input or output. You can output value, you can receive value as well. And we already have done this. We have already done this. You remember where in the course we already did that? PT5. So we already did that. So in PT5, you remember PT5 is here, one of the pins here. We used the PT5 as just a general pin. It was not input capture, it was not output compare, it was not IRQ, it was not RTI. It was a general pin, right, to generate a square wave. Is that okay? So let me tell you the conclusion before I give you more details. So conclusion is, in the timer system here, guys, we have 8 pins, right? 8 channels. Every channel you can program it input capture or output compare, right? Or you can, as I'm kind of explaining here, you can make it like IRQ, or it can be like RTI, or it can be a general pin like pin port B, port J. You can connect LED, you can connect a switch, you can connect a buzzer. You understand what I'm saying? Any questions? Now let's go to details. This is a big picture. Any questions? Okay. I'm gonna start with the counter here, because this counter is gonna play a major role for help input capture or output compare. Okay, so how is gonna play a major role? I'm gonna tell you, but I'm gonna tell you the idea. The idea is that, look here, guys, how I can measure the time from here to here. How I can measure the time from here to here. Is that okay? Also, when this one is high, I want to make it low after, for example, 1 millisecond. I want to make it low. How I can measure this 1 millisecond? So I need some way to measure the time here and measure the time here. And this is the counter. The counter will help me to do that. How? Let me complete. Okay. So as I told you guys here, we have only one counter, 16-bit counter. How this counter works? And look from the English name, it's called counter. It's called counter because it's counting, right? Otherwise, it wouldn't be counter. It's counting, right? That's true. So the idea of the counter is, it's like, it's a circuit counter, 16-bit, and this circuit should have a clock here, clock. So this circuit should work by a clock. Every cycle, the counter is going to increment by 1, right? This is a hardware circuit. So we have a hardware circuit. I call it a counter. It's a 16-bit, right? 16-bit. This counter, every time, this counter, in order to count, it needs a clock. I think in digital system course, you should have designed counter, I guess. Okay, anyway, but it's a hardware circuit, digital circuit. This digital circuit needs a clock, right? And the idea of this circuit is, for every cycle here, the counter is incremented by 1. The hardware circuit is going to increment the counter by 1. That means this is how the counter is. Look here, guys. The counter is, in the very beginning, 0, 0, 0, 0, 16-bit, right? After one clock should be incremented by 1, 1, 0, 0, 0, and then 2, 3, 4, 5, 6. So every clock is gonna, the counter is gonna be incremented by 1. Is that okay? Until 1, 1, 1, 1. So 1, 1, 1. This should be 2 to 16 counts from 0, 0, which is, as I said before, after 2 to 16, 65, 536. Okay. So after 65,536, I'm gonna reach to 1, 1, 1. Okay. After 1, 1, 1, 1, when you increment 1, 1, 1, 1, 1, you are gonna get 0. Yeah, it's gonna roll back to 0, 0 again, and count again until 1, 1, 1. You got what I'm saying? This is how it works. Again, so simple. We have a counter. This count should count from 16, 0. Okay, 1, 2, 3, 4, 5, 6 until 1, 1, 1, 1. After 1, 1, 1, it's gonna go to 0, 0, and then repeat again, right? And the way it counts is you need a clock. And for every cycle of the clock, it's going to be incremented by 1. Is that okay? Not only that, look here, guys. Every time the counter rules from 1, 1, 1 to 0, 0, as you see here, is going to trigger interrupt. What we call it overflow interrupt. I'm going to give you details why we need this interrupt. I'm going to connect everything together. Okay, but we need it. I'm going to tell you why. Let me say it again. Okay, so we have a counter. This counter, every time it has a clock, input clock, every cycle is going to be incremented by 1. It should count from 0, 0 until 1, 1, 1, 1, 1. After 1, 1, 1, it's going to go to 0, 0 and count again, keep counting. So it's counting all the time, right? And then trigger interrupt here, and that's what we call timer overflow interrupt. That's why, if you look here, guys, we have 9 sources of interrupts here. 9. We have 8 sources of interrupt coming from the channels. Each channel can trigger 1 interrupt, and we have 1 interrupt coming from the counter or timer, whatever you want to call it, counter. Okay, so timer overflow. You can tell from the English name, it's not difficult. Overflow, right? Because it overflows. This is overflow. When it becomes 1, 1, 1, 1, and you add after 1, 1, 1, it's going to become 0, 0. Overflow, right? This is a meaning of overflow, right? Anyway, so every time it happens, this happens, it's going to trigger interrupt. We call it overflow. Okay. Again, let me finish. For sure, I'm going to use this one. Okay. You will understand why you need this overflow. But again, so what I'm saying, guys, is that we have 1 counter. The system here has 1 counter. Okay. As you see here, the system has 1 counter. This counter is connected to a clock source. I'm going to explain how it can get this clock, and this clock can control how fast this timer can count. How fast? Based on higher frequency means it's going to count fast. Lower frequency is going to count slower. Okay. Anyway, so every cycle is going to be incremented by 1. And now, this is how it is. Now, I want you. I explained separate pieces. Separate. I need you to connect them together. I'm gonna tell you how I connect it. For example, so we have something called input capture. We have something called output compare, and we have something counting here. All the time it's counting, just counting. Can you link? Is there a link between them? For sure, there is a link. This counter should help the input capture, should help the output compare to do their work. How? I'm going to tell you how. Okay, very simple. Look here. If I wanna, I told you here, if the clock, if I'm going to use clock if hertz. So if hertz, whatever f is, so I'm going to use f hertz. This is the clock of the timer. Is that okay? That means every cycle should be 1 over f. Every cycle, that means 1 over f. That means every count is going to take 1 over f time, right? So here, to count from here to here, I need this time. To count from here to here, I need this time. To count from here, I need 1 over f time. So this is the time for count. Is that okay? Okay. So how this can help input capture, output compare? It's going to help. I'm going to tell you how. Look here. Let me go a separate slide just to make it easy. Okay. Look here, guys. If I have, this is input capture. I just want to link. I want to link input capture to the counter. I want to teach how the counter is going to help input capture to do its work. Right? That's what I want to say. Look here, guys. For example, I want to measure the time from here to here. How I can do that? Okay. Counter is my friend. Counter is going to help me. How? I'm going to tell you how. Look here in the counter, for example, this counter should count from 0, 0, 0 until 1, 1, 1, 1, 1. Is that okay? Now, I'm going to look here at this time. What was the count here? The count here was 700. And when this one come, what was the count here? It was 750. That means from here to here, the counter counted 500 counts. Oh, sorry, 50 counts. This is the time I want to measure. This is the time. So the time of the signal from here to here is equivalent to 50 counts. But this is not time. Time is measured in second or minute, or it's not number of counts. It's very easy. You can convert the number of counts to time. How? I told you every count, the time of each count is 1 over f. So it's going to take 1 over f time. 1 over f is second or microsecond or millisecond, whatever. So it's going to take 1 over f to make 1 count. So if the timer was able to count from here to here 50 counts, that means the time from here to here should be 50 times 1 over f second. That okay, guys? Okay. Again, what's important here, you should understand how the counter is going to help the input capture. Is that okay? Okay. Now, I'm going to also explain how the counter is going to help also output compare, right? How? I'm going to tell you how. It's the same idea. Look here. Here, I wanna generate a signal from here to here, for example, 300 microsecond. For example, after 300 microsecond, I want this one to go down. Okay. So in this interrupt here, in this interrupt subroutine, I told you here we have interrupt subroutine. In this interrupt subroutine, right? I have to say, I have to decide. I have to say, please, after 300 microsecond, please toggle. I have to do something like that. I have to say here, for example, I want to go here, for example, for 900 microsecond. So here in this interrupt, I'm going to say, please, next time toggle after 900 microsecond. This is how output compare works. Just give me just 1 minute to finish. Okay, this part, just 1 minute. Okay, guys. So this is how it works. We have interrupt here, and this interrupt here, I'm going to say after 300 microsecond, please toggle. And this interrupt here, I'm going to say, please, after 900 microsecond, toggle. How I can say it? I'm going to tell you how I can say it. If I know the time for, again, is going to be relative. It's going to be relative to the number of counts. Again, right? For example, if I know that the time for one count is 1 over 3 microsecond, okay, that means from here to here, we're gonna count how many. So this is 300. So here we should count 900, right? So it should be 900 counts here. Okay, that means I'm gonna say if the counter right now is, for example, number 7. Please counter when you are 907. I want this pin to toggle. You understand what I'm saying? So number 1, here I have to convert the time to number of counts, right? Because the counter is counting. So I'm going to say currently it's number 7. So please, after 900 counts, please toggle. Why 900? Because 900 is going to be equivalent to 300 microsecond. Okay. Again, I'm going to give you the details next time, but I just want here to understand how I'm going to link this counter to the input capture or output compare, because everything is going to be relevant. How many counts, number of counts. So if you want to measure the time in input capture, this time is going to be number of counts, right? Same thing. If you want to generate a signal this way, I'm going to say I want to toggle after 500 counts, 600 counts. So every time. So here you are going to get the time and number of counts, and then you can convert the number of counts to time, right? When you want to generate a signal, I have to convert the time to number of counts, right? And the number of counts, I'm going to use it in my program. I'm going to tell, please, next time toggle after 900, or after 700, or after 1000, whatever. Okay. So you need to convert between counts and time. Anyway, I'm going to explain later in details.